We're actually going live like now, so
No, no,
start
no.
behaving, Lane.
I'm probably, if you want to sell probably 3 runs. And three would work.
Dave says he completely forgot the meeting was tonight. Yeah, sure.
Well, I'd say if you want to come get it.
I don't even know if they have any running plans.
Yeah.
It's hard to get some days.
Having all these conflicts.
Yeah.
Well, not that.
Normally I have some.
Here's what.
Okay, folks, we'll get started. Let's see. Quick review for the astronomy enthusiasts of Lancaster. A little bit of a tongue twister. I'm Lane Davis. I'm the current president. Tom is our treasurer. James is off to Maine, our secretary, and Rob is our vice president. We have several things planned for tonight. But first, how many people here have read the story in the news about some giant comet coming through the solar system? Nobody?
I saw the headline, but.
I hate, comets, it's always tough to know what a comet's going to do. I've forgotten what famous astronomer it was that said he'd rather bet on a racehorse than a comet in terms of predicting what they're going to do. But this one is actually pretty easy to predict. Famous last words. It's coming in from the Oort cloud. That's certain now. Who could give a quick description of what the Oort cloud is? All right. Picture our solar system. Forget the planet. The sun, right there in the sun. It's surrounded by a a sphere way out there of comets that was postulated by Jan Port, who was an astronomer. I think he died recently. And hence his name was put on. And the reason he predicted it was occasionally we'll get a comet coming through the solar system that's not in the plane of the solar system. It's the plane formed by the sun and all the planets. Although, as far as I know, correct, if anybody knows better, correct me, we've never directly detected the Oort cloud. But we have detected over the years a number of comets that came in from the Oort cloud. So if this is the plane of the solar system, they could come in from any angle, from above, from below, whatever. And this comet seems to be one of those. It's big, but don't believe the measurements. Anybody know what the typical size of the core of a comet is? 5. I've seen them as small as down to about 1 kilometer, up to maybe 3, 4, 5 is not atypical. So they're not very big is the point. And the only reason we get excited about them is to get close to the sun. All the volatiles, such as water, methane, and other things like that, they sublimate out of the comet and form this huge coma. It's really just a water vapor and gas cloud around it, and this long tail as the sun pushes that gas cloud away. It'd be nice if this comet was going to do that, but it seems very, very unlikely because most comets, they have to really get as close to the sun as, say, Mars is to start performing like that, start developing that coma, that cloud of vapor and gas around. This one isn't coming anywhere near Mars. In fact, it looks like it's not going to get any closer to the sun than Saturn. And Saturn's pretty far out there, about 10 astronomical units, or in other words, about 1 billion miles. So that's factor number 1. But still, we occasionally see a comet that surprises us and gets bright and big. Although I've never seen them that far out. The other problem is we're not going to see it. It's not going to get as close as it's going to get to the sun, even though it's as far out of Saturn, until 2031. So I don't know, some of us probably won't be here by then.
We will forget about it missing.
Yeah. So I've had several calls over the last week about people just reading articles in newspapers or seeing it on CNN was doing a program. It's nothing to get excited about. Long time away, and it's way far out in the solar system. Any questions about any of that?
So is it the sun's gravity that's pulling it from the cloud? And if that's the case, why aren't we being bombarded by these comets? And why is it just, if it is the sun's gravity that starts the process, why is it just occasional?
We know. Okay. We have the Oort cloud. It's a sphere, sun of the sun. But in the plane of the solar system, which is like a disk around the sun, a little bit further out from that is something called the Kuiper belt. And the vast majority of our comets come from the Kuiper belt. And it's like a donut around the outer edge of the solar system disk. We know they're coming from that because, number one, we've got a number of images of them out there. You can tell by the way they came in, they always come in the plane of the solar system. Those comets in the Kuiper Belt, and they're much, much closer to the Oort Belt. Those comets in the Kuiper Belt are usually pulled in by one of the gas giants, either Uranus, Neptune, or Jupiter. Because they have combined, I think they have close to 1% of the gravity in the solar system. The sun's the other 99%, the other planets just don't count at all. There's hardly any gravity. But they have just enough that every once in a while pull one of those comets in. The Oort cloud, nobody's clear about what makes those come in. So we have a lot to learn, a lot of things.
I think they suspected that millions of years past, sometimes a star would come very close and then just mix everything up. So the Earth would get bombarded. They kind of track some periods when this could have happened. So.
Yeah, there are patterns there. They're not repeating patterns. The point is that that seems a likely explanation for some of the heavy comet bombardment that we had in the past. But why it's not happening now? The solar system is not chaotic anymore. You know, in the beginning,
It's
it was
only
very
planet
chaotic.
Earth.
It was a real mess. It was like a whole bunch of bumper cars running around slamming into each other. You know, it's pretty quiescent, pretty stable. Thank goodness.
The way I like to explain that to my students is I get this big, what we call a gravity well or black hole. It's just a large amount of lycra that is around a big circular thing of tent rods, if that makes sense. And so you put a heavy ball in the middle, and so it makes this curve like you've probably seen at science centers where you throw a quarter down and it goes in. But what you can do with that is you have that curve, but then you take a bunch of marbles in one hand and a bunch of marbles in the other hand, but a few less marbles in the other hand, and then you throw them in opposite directions. And so what happens is most of them hit and fall, boom, right into the center. But by the end, by a couple seconds in, when most of them have hit, collided, and fallen to the center, there's a few that are left over that are still orbiting around the center. And so in that sense, the ones that are still out there are the ones that are still sort of orbiting around the center. There's nothing left to hit and make them dive back in. Maybe that's one of the reasons that one is coming in. Or I think somebody's mentioned a star passing by or us passing, but all little things can make that happen. But most of the exciting part of our solar system forming is done. All those crashes are mostly done.
Except for the next asteroid that's going to destroy Earth. Other than that, it's pretty cool.
Okay. Tom, how about the telescope round?
Okay. Well, we had another donated telescope. This is the second one. This is a 4.5-inch Bushnell. So 3 club members were interested. So I got 3 tickets in here. Stan, your name isn't in here, so you just reach in here and grab one of them.
I can't even find them. Okay, there. That one?
Yeah.
It says Elaine Olson.
Okay. I'll let Elaine know she's not here. And I'm sure we'll get some more donated ones, so anybody who wanted one's probably going to get one eventually.
Okay, Ron.
Want me to go?
You're up.
All right. Usually I have a nice fun video to go along with this, but it's summer after COVID, so I'm not doing anything with technology. It's cool. So I'll tell you, I did put something together, and I did do a 1-month podcast with this group called 360 Days of Astronomy. If you're into listening about stuff, listening to podcasts, they have a podcast every single day. They've been doing this for 10 years. I've sort of given mine to them once a month to fill up their schedule, but they have even cooler people like Fraser Kane and other actually famous astronomers who actually know what they're doing. So, but what I do have a couple things to think about for just getting out there and observing for this month. We've got Mars and Venus. Okay, anybody know where you can see Mars and Venus? What direction? West, right? They're the sunset planets, right? Now, Venus, how many of you have actually seen Venus lately? I mean, it's gorgeous, right? Especially in the dusk when it's, still sort of blue or get a little nice sunset there. Venus is basically staying about 15 degrees above the horizon in the west, so about a fist and a half, or if you do this, it's about 15 degrees at arm's length. It's about how high it's going to get, I think for a couple months. And Mars is technically there too, although it's going to be harder to see because it's a lot dimmer. You kind of have to wait for after dusk, and by that time Mars is pretty much set. So you kind of need to know what you're looking for. But yeah, this is the last chance to see Mars. Not that it looks that great in the telescope on the horizon, but you can see it. Now, with those two, there is some excitement with those two. From July 11th to the 14th, on July 12th, Mars and Venus are going to get within, I think, less than a degree, in fact, maybe about half a degree apart from each other. So that's on the 12th. And also the moon is going to be sort of hanging out with them at that time as well. So if you get out after sunset, but before 9:30, look west. I think the easiest one to find is going to be Venus because it's brightest. Now on the 11th, Mars will be only a pinky width to the left of Venus. And a 2-day-old crescent moon hangs out about 3 finger widths to the right at about the same height. So Mars and Venus, and then the moon over here. Okay, the moon's going to be tough to see because it's very, very thin. Then the best night is likely the 12th, when Mars and Venus are half as far apart as the previous night, and the moon is thicker and easier to find, just 6 degrees up and to the left. So you'll see Mars and Venus, and then the moon will be up and to the left a little bit. And Leo's up there as well, looking like it's actually eating all of them at that time. And then let's see. Yeah, the next 2 days, I mean, the moon's still in that area, and Mars and Venus are still close. So as long as you get out there after sunset, July 11th to the 14th, you're good. Just make sure you have a nice view. Don't be trying to look over your neighbor's house or a mountain. Right? You got to get that nice clear horizon. Anybody know about the other 2 planets that are looking good this month? There's only 3 left.
I'll pose it as a quick.
Yes.
That might be right. Last night I couldn't sleep. I woke up about 3:30 in the morning,
Yep.
and it's really the best time to go out. I walk outside in my yard, do a reset, and I'm looking pretty much due south, about 40 degrees up.
Yep.
I'm thinking Jupiter.
Bingo.
It was
You got it.
clear as a bell.
Yep. Absolutely. And not too far from that was Saturn. In fact, Saturn was a little bit up and to the right of that.
Okay.
Which was a little bit harder to see if I'm correct. So here's what I got. I've got Saturn is rising around 10:30, so it's all over in the east at 10:30, and then Jupiter rises about an hour later. And so if you're looking at night, if you're staying up and not waking up at 3:30, you're going to be looking more toward the east to find these guys. And that's at the beginning of the month. By the end of July, Saturn and Jupiter rise about 8:15 and 9:15. So basically during dusk. So this is when they start transitioning into, you can see them all night. But then in the morning, if you're up in the morning, you're looking more southeast. And you're going to see Saturn is going to be to the right and a little down of Jupiter. So if you go out the same time.
If I can't sleep tonight, I'm there.
There you go. Jupiter is the very bright one, and Saturn will be to the right and a little bit down. And the moon joins them from the 22nd to the 26th. Just look after 10:30 in the southeast, or before dawn, you're looking southwest. Just find the moon, and Jupiter and Saturn will be nearby. I won't go too much into the details, but basically, The moon is in between the planets on the 24th, right in between. So 23rd, it's off to the side. 24th, it's in the middle. 25th, it's off to the other side. And that's really what's going on. We're getting to the point where observing Jupiter and Saturn are going to be really good in terms of having a lot of time to see them. I don't know about seeing and all that stuff. Lane would be able to tell you more about that. But they'll be out there for you. Okay? Any questions about what's going on this month?
As ever, I think probably the weather we're enduring right now with the humidity is going to be an offset to being able to see them really well, right? I mean,
I would.
Even at
That's
night,
that's
middle of the night.
my understanding. Lane, what would you say about that?
Usually humidity steadies the air.
Oh.
So you get better seeing. So those hazy summer nights are usually, you can see the most detail on the moon and planets and such.
Not for deep sky stuff.
Okay. So for the deep sky stuff,
Transparency.
okay.
Right.
Okay. So the summer is steady air, but is it a little bit brighter, a little bit less transparent?
Less transparent.
Anybody see anything cool?
Haze.
Nice.
Yeah, you can call that cool.
Yeah. I've been enjoying watching the fireworks and having my son point out Venus to anyone who's nearby. All right. Okay.
Okay, we might as well get started with the main presentation tonight. Let's see if I know how to work this thing. Yeah. Everybody see the red dot?
Yep.
Next, I have to find my presentation. Wow. I'll do it this way then. Using computers for over 60 years, you would think I would know how to.
COVID wiped out your memory.
Yeah. That's about it.
The joys of technology.
They keep moving stuff around on you too.
It's going to,
Well, they've succeeded in confusing.
you can figure out how to make something work. Come out with a new version.
All right. The subject is stardust, or interstellar dust, cosmic dust, space dust. It goes by many different names. But at the core of all of it, it's the stuff that we're made of. And I don't just mean us as people, but the earth, the the other planets we've been talking about, and so on. And we've all seen it in one form or another if you've seen the Milky Way. Could somebody get the lights, please? Good. All right, how many people have seen the Milky Way like this? Yes. You have to get to a pretty dark space to do this. This picture was taken by a friend of mine down in Florida. He lives in the middle of nowhere along with the mosquitoes. And he loves doing this kind of thing. And when you look at the Milky Way, first of all, you see a lot of bright stuff. These lights around here, over here, but it's accompanied by all these dark regions. And those dark regions, anybody know what those are? Okay. It's a combination of gas, almost entirely hydrogen gas, clouds, thick clouds of hydrogen gas, and stardust, or interstellar dust. Okay, that's what's in these dark areas. And by the way, that's Jupiter down there. This is from a couple of years ago. Okay, let me explain something here. When I was putting this slide set together, I kept reorganizing it and reorganizing it and reorganizing it. So in some places, it's a little disjointed, but bear with me here. Edward Emerson Bernard. How many people have heard of E. Bernard? Okay. Pretty famous astronomer. Came from and this isn't an unusual story. Back in the 1800s, he grew up in poverty, had hardly any formal schooling at all. When he was old enough to get a job, he became a photographer's assistant, got pretty good at it, and then decided he wanted to be an astronomer. So he got a job at Vanderbilt University down in Tennessee, is it, I think, yeah. Just working at the observatory there. And took a few astronomy courses, and eventually started combining his photography skills with astronomy. So he was one of the earlier astrophotographers. And one of the things that is fun is he built a photographic atlas of those dark clouds that we just saw in the Milky Way. And he identified 349 of them. A good example is B33, Barnard 33. Does anybody know what object that is up in the sky? Yes. The Horsehead Nebula, yes. And the reason he was doing this is there was a controversy going on at that time. Nobody knew the answer of, are these dark clouds voids in space where there are no stars? Or are these clouds something physical that's there that's blocking the stars behind them? In other words, why is it so dark? Because the rest of the Milky Way seems to be filled with stars. So he set out to try to solve that. And without going into any detail exactly how he did that, with his photographs, he was able to convince the astronomical community that these were actual objects there. So that was like the first time that anybody had actually tried to identify what these clouds are. They didn't know the substance of the clouds. They didn't know what they were, but they did know there was something there. It was not simply a void in space where there happened to be stars. Well, nobody paid much attention to it. It was kind of one of those things where the astronomical community said, well, okay, we know what they are now. Let's get back to what we were doing before. And it was kind of a long time before anybody tried any further study, further analytics. And a lot of that had to do with waiting for technology to catch up, where they could start figuring out what these clouds were. Now, here are 3 galaxies. Does anybody know what galaxies these are?
Leo triplet?
Yes. It's called the Leo triplet because it's in Leo, the constellation of Leo, which is at its highest point March through June, something in that realm, high enough in the sky. Almost any size telescope will show, let's go back to that, will show this one and this one. And a little bit larger telescope will show this one. Notice though, these dark areas. Okay, here, there's a dark area there, dark areas scattered through this one. Those are all gas and dust clouds. So the point being that it's not just the Milky Way that has these things. Lots of other galaxies do. Well, the question is, why do they have that? Dust is a product of stars. Interstellar dust grains have their origin in the material ejected by a dying star. Does anybody know a good example of a dying star?
Isn't Betelgeuse one of those that's going on?
Betelgeuse, exactly. You're a good straight man. We'll get to that in just a second. Let me catch up to where we are. I gotta see my notes. All right. There are lots of stars around, and typically that produce dust. And they typically are the red giant stars, which is in phase of the life cycle of a fairly ordinary star. And they're outer, when they swell up to form a red giant, of course they cool down. In other words, if you take a certain amount of heat energy, which is crammed into a star, and you expand the size of that star, it cools down because you've got the same amount of energy spread over heat energy over a much bigger area. So of course the temperature drops. So they form in those cool environments, like the atmospheres of red giant stars. Dust forms. It's released into the interstellar medium by radiation pressure, stellar winds, things like that. As you all know, our sun has a stellar wind. It's pushing particles, usually charged particles, out of its atmosphere. And we live in that kind of environment. The Earth is always plowing through that stellar wind. And all stars are like that, but it gets really intense as the star is dying. A really good example, as was brought up, is Betelgeuse. How many people have seen Betelgeuse? Ryan. It's a red giant star, and what happened to it about a year ago? Does anybody remember? What?
It was dimming.
Yes. The brightness of Betelgeuse suddenly dropped a significant amount. In fact, there were a number of people who noticed the difference with just their eyes. You didn't have to measure it instrumentally. And everybody was puzzled about, okay, why is that happening? In other words, is there something going on inside Betelgeuse itself? It shouldn't be, but you know, we learn new things in astronomy all the time, just like any science. So it could be a possibility there's something going on causing Betelgeuse to actually dim. But the alternative was there may be a cloud, once again, gas cloud, dust cloud, passing between us and Betelgeuse. The measurements that we've gathered since then suggest very strongly that it's actually dust in the atmosphere of Betelgeuse itself that was the dimming event. And as you can see, it's getting released into the interstellar environment. In other words, getting pushed out of Betelgeuse. And so that particular set of dust that was dimming Betelgeuse got pushed further out away from the star, and hence it brightened up again. And this is not an unusual event by any means.
For the record, how far away is Betelgeuse in light years?
I don't remember.
So it was actually happening, whatever, years ago.
Hold on. No, not Bethany Beach.
I assume you're looking it up.
642 light years.
So
Okay, so this happened 642 years ago.
Mhm.
And we're just finding out about it today. All right. So when we look at the Milky Way, we have the technology today to measure what makes up the Milky Way. In terms of mass, 91% of it is stars. Okay, 9% of it is gas. That's a lot of those dark areas we saw in the Milky Way. They're predominantly gas, and we'll get into that a little bit deeper. But only 0.09% is dust. That's one of the remarkable things about dust. There's not that much of it compared to all the other things in the Milky Way, but it has a disproportionate effect on how the Milky Way behaves, what it does. So, what does it do? Well, and we'll get into more detail here. First, it helps build giant molecular clouds, which is the hydrogen clouds, the gas clouds you saw in the Milky Way, those big dark spots, by providing a surface on which two hydrogen atoms can bond. And this is the first place where we'll talk about chemistry goes on in space. Okay, space is a very cold environment, and not a lot of chemistry happens in a very, very cold environment. But under the right circumstances, and dust literally acts like a catalyst. Some chemistry can occur. And in this case, a giant molecular cloud is talking about molecular hydrogen. All the dark stuff, or almost all of it, that we saw in that shot of the Milky Way is molecular hydrogen. And that's H2, or in other words, two hydrogen atoms bound together. Right. And those are the clouds of gas that make stars in the end. So without dust, you really can't make stars. It helps build stellar nurseries. Here's the other thing it does. Those giant gas clouds, we've talked about these before. What's a really good example of a giant gas cloud that's making stars? What? The Orion Nebula, exactly. Something that you can see in the constellation of Orion every year. Those stellar nurseries wouldn't be happening, it wouldn't be creating stars if it wasn't for the cooling effect of molecular clouds that dust has. So in other words, you have a molecular cloud, one of them, say, bumps into another, creates a more dense spot, and it starts collapsing. The gravity of gravity of that gas takes over and starts pulling the cloud together into a smaller and smaller space. But that wouldn't continue under natural circumstances, because what would happen is, you can imagine, you've got all those atoms in that cloud bumping together, and they're creating heat when they do that. And they'll make enough heat that it will will stop the collapse at some point. But dust, interstellar dust, has a cooling effect on all that. We'll talk about that later. Also, planets. Oops, let's go back here. Newborn planets. The Earth is made up of interstellar dust. Right? We're not made up of hydrogen gas. So hard planets, rocky planets as you think of them, they were made up by interstellar dust. They're not made up by hydrogen gas. What's a good example of a hydrogen gas planet in our solar system?
One of the gas giants, I would guess.
Yeah, Jupiter's a good example.
Yeah.
Okay, so the point is, planets can get formed by gas, they can get formed by dust, or sometimes a combination of the two. And that wouldn't be going on. But the hard planets would be formed without dust. It also pushes newly forged elements into other star formation regions. So as these stars blow off this dust that formed in their atmosphere, push it out into space, it eventually, over a very long period of time, will pass through another gas cloud and maybe form stars there. And each time that happens, you have a new generation of stars. Now, we already mentioned chemistry in space. Another example of chemistry would be if hydrogen can alight on a dust particle surface, it can pair up with a hydroxide ion to form water. We know water forms that way. You'll see how this happens in just a moment. But it can also, dust can also lead to blunders. In other words, it's involved with a lot of the critical things going on in the Milky Way, such as the formation of stars and the formation of planets. But it also, as you can imagine, everywhere we look around us up in the sky, we're looking through a veil of dust because it's everywhere. You wouldn't notice it with your eyes, but if you're using scientific instruments, you will be affected by it. So if you're trying to measure the brightness of a star, for example, there are many reasons to do that. You have to take into account any intervening dust between you and that star, because that dust will do two things to the star. It'll make it a little bit redder and make it a little bit dimmer. Okay? If you don't take that into account, your measurement won't be accurate. A good example of a blunder, and a recent one in the scientific community was, and I don't know how many of you remember this, but I remember reading about it. How am I going to describe this? The easiest thing to do is read it. The team of a project known as BICEP, which is the background imaging of the cosmic extragalactic polarization, that's a big mouthful, announced that they had found an elusive signal from the dawn of time imprinted in the cosmic microwave background. It was a remnant glow from the time when the entire universe was about 3,000 degrees Celsius. We'll skip that part. The signal looked like one that theorists expected to have been made by the echoes of gravitational waves released in the epoch of inflation. Now, inflation is a theory. It's probably a pretty good one, but it's still a theory that the universe expanded very suddenly for a brief moment of time right in the beginning. And there's a lot of reasons to believe that happened. But these guys thought they had found proof of it. In reality, they had to retract that later on because the signal was actually from interstellar dust in the Milky Way. They had not taken that into account. So it's like a double-edged knife. Dust does a lot of things in the universe. It particularly in our galaxy and other galaxies. But you also have to be careful as an astronomer about how you take it into account. So how do we see interstellar dust? Let's say there's a star here, and there's a dust cloud here. And we're looking at it through a telescope down here. So we're looking at that star. So what happens is, in terms of, let's see, intensity. Okay, here, if we were looking at it before it entered the dust cloud, we would just get a classic black body spectrum. We would see stellar absorption lines here. And this, now we're talking about spectroscopy, a very common tool in astronomy. But when we look at it, all that data would be exactly as we measured it. But if it's passing through a dust cloud, it gets modified. The slope gets changed. Here's the original slope of the amount of energy coming through it. The absorption lines are still there, but red light slightly reduced and blue light is greatly reduced. And what happens is, and I'll get into a favorite subject of mine. When we look up at the sky at the sun, when you glance at it, what color is it?
Yellow.
Right. Why is it yellow? Is it actually yellow?
No,
Right. What color is it?
I don't know, but I remember you talking about it before the meeting started.
Very good. The answer is, if you ask an astronaut what color the sun is, they'll say white. It is a white star. And our atmosphere renders it yellow. Right? Because the type of gas, mainly nitrogen in our atmosphere, scatters blue light more than it does, say, red light. And the net effect is, that's why the sky is blue. All the blue light coming out of the sun gets scattered all over the sky. And when you take light, which of course is all colors, and you subtract blue from it, you get yellow.
Lane,
That's what's going on.
Lane, in all the textbooks that I've had, they said the sun is a yellow G2 star.
Yes.
Why would the textbooks be calling it a yellow G2 star? And I would assume,
Because that's where the peak energy is put out.
okay,
Okay.
but still
So
to our
the
eyes.
key is our eyes.
Okay,
We're looking at it through our eyes.
The G1 and G2 are actually white. The textbooks are wrong. I'm serious.
Yeah.
I'm serious. And they have revised that recently because it's only when it gets to the G8, G9 level that it becomes more of a yellowish.
Good enough for public school education.
Right.
Okay. So a dust cloud. Push the right button. A dust cloud kind of acts like our atmosphere. It scatters blue light. So the net effect is there's less blue light coming through the cloud from that star. So that could be a very blue star, but we won't see it. Our instruments down here at the telescope won't see it as much blue as it is. Here's the blue part of the spectrum here. Notice it peaks out in the blue. The maximum amount of energy coming from the star is definitely in the blue zone. Down here, not so much. It's probably looks more reddish than blue. And without going into what you would do with these absorption lines, that's how you can tell if there's dust there. We have to measure how much of the dust lies between you, your instrument, and the star, and you have to take that into account. If you don't, that blunder I talked about is a good example. Let's see. Right.
So it has nothing to do with refraction. And of course, it has nothing to do with the redshift effect.
Correct. Correct. It's
It's
just
not really
scattering.
refraction
It's just scattering of light.
because of the chemicals. Like, like,
In our case, nitrogen.
Right.
So here's a good example. This is B68. Barnard identified it, he photographed it. This is from years later. And B68, if you just take a normal image of it, looks like this. Okay. You don't see any stars there. But there actually are stars behind that cloud. And if you image it with an infrared camera, you can see the stars behind it. Okay. So we can use technology to look through these clouds to a certain extent. All right, so what does dust look like? Well, a grain of interstellar dust is composed something like this, typically. There's a small hard core, right? This is the part that was produced by its parent star, the star that made it. Microns across. How big is a micron, folks? Oh, come on.
I was going to ask you.
A millionth of a meter. Pretty darn small. And it's made of silicates, meaning silicon and silicon compounds. It's made up of carbon and carbon compounds, and there could also be iron and other heavier elements in there, crammed into that little area that came off the star. Now, at the same time, there's usually a mantle around it, and it's usually ices of various types. Carbon dioxide ice, water ice, other things. Right? And then, and those things accumulate on that core. And then on top of the ices, sometimes there's a surface of simple organic compounds. And this is a good example of chemistry occurring in space. But this thing's still pretty small. What does it look like? Something like that. This is a real shot of interstellar dust. Particles brought back by one of the space probes we sent out in the solar system. And if you look at it carefully, it just looks like a pile of rubble. And that's exactly what it is. Space dust is, it's properly, if we were talking about Earth geology, it would be called a conglomerate. It's just a bunch of things that kind of stuck together very loosely. And it's easily split apart. It's easily destroyed. And we'll talk about that a little bit. But that's what a grain of one of these things looks like. Actually, the grains are these little pieces here, here, here. There'll be another one. They're clumping together. And when a solar system is formed, they keep clumping and clumping and clumping together until they get big enough to form a planetesimal, which something we think's like looks like an asteroid, and eventually they can form a planet. So, how do we use, other than just trying to avoid embarrassing claims, by allowing for what interstellar dust to our measurements does? There are other uses for it. First, interesting thing about the dust is it will align itself with with any magnetic field. So astronomers have been able to map a lot of the magnetic fields in the Milky Way by looking for polarization in their measurements of interstellar dust. It also pinpoints the locations of nearby star-forming regions. And an interesting thing is, about 10 billion years ago, which is roughly 3 or 4 billion years into the life cycle of the universe at the moment. If you look at a galaxy back then, and we can do that with, we can do it with Hubble, we can do it with a lot of ground-based telescopes, and we'll do it even better with the Webb Space Telescope if it ever gets launched. Because you have to look, and we're getting back to your point about when you look way out at very distant galaxies, you're looking way back in time, and you're out in what they call the Hubble flow at that point, among other things. So in other words, it's receding from us very quickly at that point. So the light that's getting here is heavily redshifted. In fact, it may be shifted all the way down to the radio wavelengths because of that. But we look at those galaxies, and it's how many have you seen some of the deep Hubble Deep Field and others where they point out a galaxy and it just looks like a little red blob, nothing more than that. That's a heavily redshifted galaxy, so it's very far away. We're seeing it as it was like 10, 11 billion years ago. And you can't see the galaxy itself. And what you're actually seeing is a giant dust cloud, a cloud of interstellar dust that envelops the galaxy. And as far as anybody can tell, the reason that cloud is there is because that galaxy is making lots and lots and lots of stars, and those stars are creating lots and lots and lots of dust. Once again, we have to take into account what it is we're looking at. In other words, yeah, that's interstellar dust and that tiny little blob, and it probably forms a galaxy. There's a galaxy inside it somewhere. And that means that way back then, galaxies were making a lot more stars than they are now. Milky Way right now is making, I think, about 5 new stars a year. And the estimate is that based upon the measurements made with the really big telescopes looking way out, and therefore further back in time, is that they were probably making close to 5,000 stars a year. Okay, so that's a lot more, about 1,000 times more stars. And so that's one of the things we've learned about cosmic formation from studying interstellar dust. In other words, if we hadn't gotten good at detecting interstellar dust, we probably wouldn't have been able to determine this.
So I hope it's not going too much off topic, but given what you just said, production is way down. If you look at the universal process as a chemical reaction, are the processes dying? Why is it slowing down? There's not as much chemical reaction per square inch, so to speak.
We'll get to that.
All right.
Okay. So here's what we know about the life cycle of dust, and then we'll talk about your question. Okay, so stars, they age, they die. All right, they release these dust grains that were created in their outer atmosphere. Heavily documented, lots of measurements. We know that's going on for sure. In fact, we've even measured the volume of dust that's being produced. The dust grains, of course, get blown away by the stellar wind, and they mix in with the interstellar medium. Interstellar medium just means the space between stars. eventually drift into these diffuse clouds. Remember, they're drifting into those molecular clouds, hydrogen clouds we're talking about, those big dark spots we see in the Milky Way. And the dust grains coagulate. They start clumping together, as we saw in that picture. That picture probably had 1,000 dust grains in it. And they're very loosely held. But there is some mostly electrical attraction between them. It's not very strong. The gas clouds, of course, start collapsing, and the dust promotes that collapse, but by bleeding off energy from the collapsing process itself. Otherwise, stars could never have gotten started to begin with. The protostars, that is, it's not a star yet, but we crammed enough hydrogen gas into a small enough area that it's starting to really heat up and starting to fuse hydrogen in its core, which is its main energy production process. But when that happens, of course, as we all know, the gas cloud, that tiny little gas cloud that's forming the star starts spinning, because when dust collapses into the center like that, it never does it evenly. So it's going to spin in one direction or the other. And for that spinning creates a disk around the protostar. And in that disk is a lot of gas and dust. And the dust grains build up slowly into planetesimals, in other words, small planets. And those planets, as we were describing earlier, in our early solar system, they were bumping into each other and colliding all over the place, and eventually coalescing into bigger planets, until we see pretty much what we have today. Okay, and then the star that created all that goes through its life cycle, begins to die, and makes more dust. And the whole cycle just keeps going. All right? Now, let's talk about some recent
Can I ask you a question while you're on that image?
What?
Can I ask a question while you're on that image?
Sure.
So if stars are formed from interstellar dust, and interstellar dust,
No, interstellar dust is just one of the components. Stars are mostly hydrogen gas. Okay, so what they call the giant molecular clouds, which is where stars are formed, like the Orion Nebula is a star factory. That's like 99%, 99.5% probably hydrogen gas with a little bit of dust mixed.
but the stars are letting off dust as they're aging and dying.
Speak up a little louder,
The
please.
stars are letting off dust as they're aging and dying.
Yes.
So does that beg the question, which came first, the dust or the star? Kind of like the chicken and the egg.
Yeah. And that's one of the things we're hoping to solve with the Webb Space Telescope. We have to see far enough back in time, as close to the beginning as we can get.
Lane, would it make sense to say that a lot of the first generation stars were almost entirely started with hydrogen, and then
That's exactly how it happened.
okay, and then second generation stars were able to have the dust
Yes.
because those first generation stars were able to explode and give off
Right.
the stuff that they had. So the first generation stars only had hydrogen and
They had
a little bit of
hydrogen,
helium.
a tiny amount of helium, and a very small trace of lithium.
Yeah.
Is all they had to work with.
Right, they didn't have dust in the first generation. Right. Okay.
I think the key here is that's why the first stars were enormous. Because, as Lane had pointed out, you have to cool that gas down. So it overwhelmed, to be able to have gravity had to be so much gas, hydrogen gas, enormous quantity, to actually overcome not having to cool, because it said you're pressing in, friction starts, and you get hot. So they were enormous, and they only lasted a couple million years. They blew up. Then dust started. As next generations came, as the gas cloud came, as you pointed out, the dust particles cooled it down. So then you get multiple stars, like clusters and everything else forming, and these stars formed and lasted longer,
And they were smaller stars,
and they were smaller stars.
like the sun. Okay. Did I answer that okay?
Thank you, yes.
Recent findings. There was a study, which means somebody went out and made a whole bunch of measurements in just 2020, last year. They proved that glycine, which is one of the building blocks of life, can form on the surface of our dust grains. Even in the absence of energy, through what they call dark chemistry. In other words, chemistry that's occurring in very, very cold environments. And let's see, they say those findings contradict previous studies that have suggested that ultraviolet radiation from the star was necessary to do this. Glycine, by the way, is the simplest amino acid, and it's a very important building block of life. So slowly, many years ago, how many? Oh, geez, I don't remember. 45, 50 years ago, I was at an astronomical league conference up at Kutztown. And I remember one of the lectures was by a chemist who talked about chemistry in space. And one of the interesting things was, in the end, he had to admit, they just don't know anything about it. So all he could do was speculate about some things. And really the problem, once again, was the lack of the technology you need to detect chemistry occurring in space. And obviously, we're slowly getting there. Like I said, we can detect glycine out there now, and even detect the probable way it was formed. So you have to take all this with, no pun intended, a grain of salt. But the point is, we're learning that there's actually a lot of chemistry going on out there in very, very cold space, which just 20 years ago, you would have been told that, there's hardly any chemistry going on except in the near environment to a star, where the star is releasing enough energy to cause the chemistry. So that's encouraging. Another one is really interesting. And this one's recent. It just came out this year. And it's pretty convincing. The measurements are really convincing. The amount of dust in the universe has been dropping for about 8 billion years. Less dust is being made. Well, in a sense, that makes sense. Because most of the part, in the early part of the timeline of the universe, it was making a lot more stars than it is. So therefore, we're making less dust now. We've already talked about that. So that kind of makes sense, but remember, these are a set of measurements, and they're saying they're finding things that don't make sense. Something above and beyond simply, we're making less stars, so what? So something must be destroying the dust faster than it is manufactured. So they built a whole bunch of computer models that told them certain things, and then they went out and made a bunch of measurements to see if the computer models were correct. And they found that probably about 40% of the dust is lost from shock waves emanating from a supernova. That's an interesting one because it gets back to, remember I showed that picture of dust, was a whole clump of interstellar dust. And I said that's a conglomerate. It's very loosely held together. And it doesn't take much energy to destroy it, spread it all over the place. And that's exactly what goes on with the shock waves from supernova. But on top of that, these guys actually measured how much dust would be destroyed by looking at those shock waves from nearby supernovas. Okay, that accounts for 40% of the dust loss that we see. What about the rest? You already know the answer, or at least a big chunk of the answer about that other 60%. Where else does that dust go? Where else does it get destroyed?
Solar wind,
What?
solar wind,
Good guess, but no. Probably not.
Some sort of natural decomposition goes on. You know,
Once again, close, but no.
Black holes suck it up.
Now, what's happening is, remember, dust gets reincorporated into the next generation of stars. And if you think about the structure of interstellar dust, the minute it gets in towards the interior of a star, it gets destroyed. So it's not interstellar dust anymore. That's probably where most of the rest of that 60% is going. But nobody knows for certain. So I think it's sometime over the next 10 or 20 years, we'll probably have some good answers there. So that gets back into the life cycle that we were talking about, where the grains build up in planetesimals, but they also get incorporated into a new star. Way back there. And eventually get plowed into the next generation of stars, which absorbs the dust and destroys it. Okay, I'm done. I hope you weren't too bored. Do we get the lights up? Anybody have any comments, anything to add, any questions?
Would it make sense with all the galaxies out there, that somewhere out there in a galaxy, there's a planet far enough away from the sun that there could be life there?
There's a galaxy out there that what?
That there's a sun in that galaxy. The sun could be close enough to a planet that there could be life on that planet.
Oh. Well, we could go on to that forever.
That's next month's presentation. Do we have any volunteers?
Here's the things we know for sure. There are a lot of planets out there, just in our Milky Way, all right? In fact, over 4,000 have been confirmed at this point. So planets are actually, we know they're very common. So after that, that's the one thing we know for certain. We're pushing the edge of technology to detect what those planets are. Are they gas giants? Are they rocky planets? Do they have water? Things like that. Over the next 10 or 20 years, we're going to get a lot better at that, at figuring those things out. So that's all we know. So if you're into probabilities, the answer, well, there must be a lot of planets out there with life on them. But that doesn't make it true. We don't know.
But are we defining life as we know it?
One of the questions. And by the way, astronomers and astrobiologists and such are still working on the issue of how do we detect life? And that gets to the core of the thing you're talking
Stops and sanitation starts.
I'm torn between two questions, but I'll go with the one I've been sort of cooking up for the last 20 minutes then. So a couple paragraphs ago, we were talking about light years away, 600 and something. Okay, so how does light stay alive? What is the energy that keeps light going for, forget 600 years, a million light years? Why does light still keep, why does it stay energized for all those millions of years?
The best way I can describe that, and anybody else that wants the answer, jump in.
Sorry.
All right, let's say I'm the most powerful man on earth. In other words, strength-wise. I take a ball and I throw it up into space. I throw it faster than 25,000 miles an hour, which is the escape velocity of Earth. Okay, why does it keep going?
There's nothing to, right, there's nothing there.
That's the key. Light is pure energy. It'll keep on going until something stops it. So we talked about that a little bit tonight. If that little photon of light hits a dust grain, what happens? Well, let's say it's blue light, high energy light. It hits the dust grain absorbs it and re-emits it as red light. But when it re-emits it, potentially it goes in any direction. Okay?
It's just a little bit hard for me to grok that something is, because it's unstopped, it's unstoppable. It doesn't decompose
No, it's
in
not.
any
It's
way.
not unstoppable.
Well, because there's nothing there to stop it.
Yeah, there has to be something there to stop it.
Right.
Otherwise, it just keeps on going. Okay, folks, we're going to straighten up the chairs and clear out. I'm sorry.
Good presentation.
Yeah, man. So, like, it was kind of understated, but
Oh, yeah.
as I
Nice to meet
expected, one of the main
Rob Webb.
components of the dust itself is carbon. We are carbon
High school
based.
teacher.
Yes.
Yep. Peckaway Valley.
Well, there's a supernova form, even the heavy next meeting doesn't have to be just carbon. It's also complex.
I don't remember my chemistry. Carbon.
Yeah, it's always almost always the first Monday or first Wednesday of the month. If you go to our AELC.us, AELC.us